First point is here the column-wise addition. Just the similar things we have prepared in case of the reduced incidence matrix, current relations. This column-wise addition, what it will give, and row-wise addition, what it will give, that we will discuss. Column-wise addition gives the current relations. Column-wise addition will give the current relations. Now look at. Column-wise addition gives the relation between the loop currents, which is Ix, Iy, Iz. I will show the loop currents. Loop currents are nothing but the tie-set currents. Is it right? Here in this particular case, if I am trying to discuss here, in this particular case, this is the loop 1, this is the current 1, this is the current loop 2, it's current 2, this is the loop 3, it's current 3. These are the loop currents. Means it will give the relation between the loop currents and branch currents. Means here, in this case, this is I1 and this is Ix. Ix is the loop current. This is Ix. This is for first loop, its current is Ix. For second loop, this current is Iy and this is Iz. But branch currents are I1, I2, I3, I4. In that way, I have taken the philosophy. Is it right? So here, in this case, the column-wise addition gives the current relations. The column-wise addition gives the relation between the loop currents, which is nothing but tie-set current, that is Ix, Iy, Iz, and the branch currents, which are I1, I2, I3, I4, I5, and I6, because we have the 6 branches. Now look at the first relation. Look at the first relation. If it is a branch number 1, then this I1, which is the branch current, I1 is equal to same as Ix, only this column. This column. This I1 is here, this is I1 is here. What is the equation for I1? This I1 is equal to Ix plus 0 Iy plus 0 Iz. Means I1 is equal to Ix is this relation. Similarly, if I am coming to this second column, which is nothing but the branch current 2 for the second branch. This I2 is equal to Ix plus Iy minus Iz. Look at here, this I2. How is this relation? This is plus 1, that's why it is Ix. This is plus 1 again, that's why it is Iy. And this is minus 1, that's why it is Iz. Similarly, if I am coming to the branch number 3, this is the branch number 3. Look at how is this column-wise addition. This I3 is equal to 0 Ix plus Iy minus Iz. This indirectly, this I3 is equal to Iy minus Iz. This is Iy, this is Iz. Iy minus Iz. This I4, current in the fourth branch. Current in the fourth branch, that is I4 in this particular case is, this I4 is equal to, how is the case? 0 Ix, 0 Iy and Iz. Means this I4 is equal to the Iz, that is the relation. How is the I5? Current in the fifth branch, this I5 is equal to, how is the case? I5 is equal to Ix plus Iy. This is I5 is equal to Ix plus Iy. And finally, if we are coming back to the branch number 6, in that case, this I6 is equal to 0 Ix plus Iy plus 0 Iz. This I6 is equal to Iy only. I6 is equal to Iy only. This is the that particular equation. Is it right? Now, in this case, we have prepared these equations. That is column-wise additions, and the column-wise addition will give these equations. I will copy this equation and I will arrange all these equations in the matrix form. Now look at. I have taken equations from the previous slide. I1 is equal to Ix, I2 is equal to Ix minus Iy minus Iz. This I3 is equal to Iy minus Iz. This I4 is equal to Iz. This I5 is equal to Ix plus Iy. And this I6 is equal to Iy. That I am trying to organize in the form of the matrix. I will start with the first. For the equation number 1, this is I1. I1 is equal to Ix. Only this element present, this is 0, this is 0. And if we are multiplying this column, this is 1 into Ix, 0 into Iy, that is Iz, means we will get the similar equation. I2, this I2 is equal to, from this equation we are preparing this matrix. This I2 is equal to Ix, Iy minus Iz. This is Ix, Iy minus Iz. This is Ix, Iy minus Iz. That equation we are putting in this particular form. And if we are putting all this equation, that is equation number 3, then equation number 4, then equation number 5, and finally equation number 6, we will get something like this matrix. something like this matrix. This here, the branch current matrix into this matrix into this current, and these currents are nothing but the loop currents or tie-set currents. There is IX, IY, and IZ. IX is the tie-set 1 current, IY is the tie-set 2 current, and this IZ is the tie-set 3 current. That is nothing but loop 1 current, loop 2 current, and loop 3 current. Means if we are organizing these equations in the matrix form, compact form, this IB is the branch matrix or branch current matrix. It is a column matrix which represents the branch currents. And if we have the 6 branches, 6 currents will be there, I1, I2, I3, I4. This is transpose of the BF matrix. What is the BF matrix? This BF matrix is nothing but tie-set matrix. Now look at, what is the row in this matrix? 11, 00, 10. 11, 00, 10. And if I am coming back to this, look at its first column, 11, 00, 10. Yes, if we are converting this row into this column, second row will become second column, and third row will become third column. Yes, if we are organizing this in the matrix form, we will get this, and this is the transpose of tie-set matrix. Transpose of the tie-set matrix. This is the branch current matrix. And this IL is nothing but the loop current matrix, which is tie-set current, which is if we have the 3 loops, now 3 tie-sets, IX, IY, IZ, then these are the 3 loop currents. With in compact form, we will get this equation, and we will use this equation for the calculation of the branch currents. When there is a question in the examination, find out the branch currents. In that particular case, we will use this formula. That is IB is equal to BF transpose into IL. But first, we have to find out this IL. How to find out the IL, that we will see in the equilibrium equation. Is it right? Then in compact form, I will discuss its compact form. In the above equation, we have this IB is equal to column matrix showing the branch currents. This BF transpose is the transpose of the fundamental tie-set matrix, which is this. And IL is a column matrix showing the loop currents or showing the tie-set currents. If we have the 3 tie-sets, there will be the 3 loops, IX, IY, IZ, and so on. This is about the column-wise addition of the current. Then if I am trying to discuss the next part of this, which is nothing but the row-wise addition. If we are finding the row-wise addition, that is similar to the KVL, that is Kirchhoff's voltage law. Look at, row-wise addition will give the relation between the branch voltages. It will give the relation between the branch voltages. This is the branch number 1, this is the branch number 2, branch number 3, branch number 4, branch number 5, branch number 6. Its voltage is V1, V2, V3, V4, V5, V6. If we are doing its summation, the summation will be 0. That is the KVL. How is the KVL? Summation of the currents or summation of the potentials in any branch or any loop, summation of the potentials in any loop is 0. That is the philosophy of the KVL. It is in the similar way. This here, it is a V1 plus V2 plus V5, which is equal to 0. That is this equation, which is row-wise addition. V1 plus V2 plus V5, which is equal to 0. How is the second row? V2 plus V3 plus V5 plus V6. V2 plus V3 plus V5 plus V6, which is equal to 0. There is a KVL for the second loop, which is nothing but the second tie-set. And finally, for third tie-set, this is minus V2 minus V3 plus V4 is equal to 0. That is the third equation. Means we have these 3 equations, which is nothing but the row-wise addition in this particular case. If we are taking its row-wise addition, and I will copy these equations and we will organize these equations in the matrix form again. This is V1 plus V2 plus V5, which is equal to 0, and so on. Here, its multiplier is 1, its multiplier is 2, multiplier of V3 is absent, multiplier of V4 is absent, this is multiplier of V5 is here, multiplier of V6 is 0. That's why if we are multiplying this row with this column, we will get this equation and equal to this 0. Means if we are arranging these equations in the matrix form, we will get something like this. And if we are trying to understand these equations, then this matrix is the fundamental tie set matrix. This matrix is the branch voltage matrix, and this matrix shows the column matrix, which is the zero matrix. Means what I meant to say, in this particular method, that is in the tie set method, its column wise addition will give the relation between the loop currents and branch currents, and the row wise addition will give the KVL equation. Look at here. The row wise addition gives the KVL equation, which is this. Because how is the KVL? Summation of the potential drops in any network or any closed path is zero. This is closed path. This row is the closed path for loop 1, loop 2, and this is for loop 3, and this is the equation in the compact form. In short, how is the procedure for preparation of the fundamental tie set matrix? First, from the given figure, we will prepare an oriented graph, then we will select a tree, then we will prepare a tie sets, and for the tie sets, we will prepare finally we will prepare the tie set matrix. And from the tie set matrix, we will get the two basic equations. One is the column wise addition, which is the equation which will give the relation between the branch currents and loop currents, and its row wise addition will give the voltage equation, that is nothing but the KVL equation. That's it about this particular lecture today. I will stop here.